Welcome to a new examination of the simulation for this peat inversion soils. Actually, we will continue with looking to this Multirun. And Multirun is, as I said before, a powerful tool, but it also is sometimes a little bit tricky. And we will continue to examine what we have achieved so far, and also to try to look to what could be the next step, step 2. Okay, we should first just now start the model, and we will then return to our peat inversion multi. That was our multi-run that was completed using 200 runs, and we're covering the same period as before, and we got sometimes reasonably good results, but not always. What I would like to do now is to examine the problems that we had with this run. And first I just make sure that I will look to the prior distribution, not actually how good the model could be. Instead, I will look to how big potential the multi-run had to describe the measurements. So I extend those ensemble to the 200 runs, so it's all the variability that we have produced. And then I look to the validation, and then I will estimate the mean value for those 200s. And I think we ended with looking to the groundwater, and that was interesting, because if I click on this ensemble for the saturation level, you could compare it with what we had from the two positions of the measurements. One position was especially beneath in the very beginning. We started here, and one was beneath and one was above. So of course we had no chance to describe the measurements if we were wrong already from the beginning. So one good suggestion here is that we should try to include the variability that we have been creating, where we are getting the broad band in the end, to also cover the first period of the simulation. So that's one problem. And another problem was we cleared now, and we should look to the soil temperatures. And the soil temperatures, they were, looking like this for the 30 centimeter, and then we compared them with the measurements, and we saw that they were a little bit opposite, good in the beginning, but continuously, systematically wrong in the end. So here we had a problem, and this problem was equal big, I would say, when we look to the more shallow horizon. Here we had a nice variability, but also here it was on the same level, all only in the beginning, and in the end we were systematically wrong. Okay, not that good. How did it look for the soil moisture? We can also look to that, and we start with the deeper horizon, and then we had a relatively broad band already from the beginning, and we could compare that with our measured at the same horizon. And then we see that here it was quite successful in covering the measured, but it was wrong in the start. So also here something is wrong with respect to the initial values. Right click, clear that, and then I look to the shadow horizon, and that's partly the same pattern, but a little bit the opposite. It is, systematically now overestimation in the later period. Started perfectly, but then it became more or less constantly overestimating. So we would like to do something to improve this. And then we do as we have been doing before, we create a new document. And before I start to add those changes in the model, I would like to do some technical things, because this multi-run is a little bit clumsy when we have also redundant variables that we are not using. We have been keeping those from the very beginning, and I would like to start now just to clean a little bit to get less data in an output list. This is important, especially if we would like to use this for making long multi-runs where we should save space on the hard disk and also reduce the space for the CPU. So I remove some of the redundant variables. So number one was an old remain, and then we have this jord first with the C that was said to be corrected, but it was exactly the same as the others. So also here I right click on that line and I remove that particular line, and I remove the next in the same way. So now we have those away from location 3, and we could also remove the same type of jordfusk from location 4. So that is done, and now we have only 10 left, and that looks nice. That is much more handy to work with than having additional 5 that is just creating confusion in this step. Okay, now we should start to think on the issues. How to adjust the range of previous parameters, add new ones, or change model assumptions. We can say some things are obvious and maybe easy. For instance, this lack of correspondence with the groundwater level in the beginning. We need another initial value for the moisture, like we had put before for the temperature. So then we look to our document, and we can go into the switches maybe, and then we see for the we can look for that. No, we can go directly to the parameters, because this model is already assigned to have a starting point for the drainage and deep percolation, as you could find in the group of soil water flows. We have an initial groundwater, and that has been put to 1 meter -1. And we have also an initial pressure head put to 60. But the most governing is actually this groundwater level. So this is a good candidate to give it a range. So I set that for the multi-run, and then I put that to dimension 2. And then we should take a method. And before we have normally been taking a type of stochastic linear change. But we have also another issue that is attractive here, and that is same as. We had already before the drain level in the Multirun setup, and now we could use that to also make that consistent with the initial groundwater level. So I click this, and then if you see now, we can take this away. If you see now those Multirun parameters, we have added this initial groundwater, but it is not said what it is the same as, so we have to adjust that as well. And then we have some different options. Actually, we can choose among all those that are in the Multirun list, but then we take it like the drain level. So this means that we don't add any more, we can say, random phenomena. We only use the random generator that we are using for the drain level to make it appropriate also for the initial groundwater. So that's an easy task. But what about the hydraulic conductivity? Will that have also strong impact on those? We have only one hydraulic parameter, and that's the air entry, but we never touched upon any hydraulics and the hydraulic conductivity especially. So I will suggest that we go to the group of soil hydraulic in the parameter tables, and then we look to these settings, and then we see that those have fixed values. We have one metric conductivity and we have one total conductivity. Both of those could be modified, and if we just look to how they looks like, you know, they are sharp decreasing with higher pressure head or lower water content. So they are quite dramatic here, and this dramatic change in the beginning is mainly related to this total conductivity, also represented by the macro pools. Maybe we don't have so much of those. Maybe this is too high, and that is now draining the soil too efficiently. So this is a good candidate. We select that for the Multirun simulation, and we can take a range from maybe 150, and we had more than 5,000 before. Maybe I think 5,000 is enough. So that's my new suggestion for this hydraulic conductivity, and we put that into dimension number 2. So that should give us more flexibility with respect to the lower boundary conditions. And we have now both the total conductivity and the initial groundwater together with the drain level, and also, so at least we have 4 parameters to create some flexibility for the water flows and the hydrological conditions. But can we do something more about the temperature? The temperature is wrong. It is absolutely too low compared to the measurements. And then my issue is that maybe it depends on how we have been calculating the surface temperature. We adapted the model using Penman-Monteith equation and the surface temperature as a function of Penman-Monteith. this Penman motif is not the most physical correct model. It is a good model, a well-established model, but still it is more realistic to use the iterative energy balance to cover this type of surface temperature conditions and surface temperature estimation. And this is of course also connected to what type of cover we have. What type of vegetation do we have in this simulation? I go to the parameter table and then I will see that we have assigned the plant as a static property, and we have, for instance, a height of the canopy, and we have a leaf area index that varies with the season. Actually, it starts with 0, have an optimum of 5, and end with 0 again. The optimum is at day 220. That's not so far away from the period in September. So the whole season is not that important, but this optimum is also a candidate for looking to the sensitivity of the vegetation cover. So I add also that, and I add that we can say in a range we have a grass growing, so it should not be too low, but I guess we could set it, for instance, from 1 to 5, and then I apply that. Okay, now we have actually 6 parameters, but only 5 that has a direct connection to random we have only we have 5 that are connected to random functions in this dimension number 2. In addition, we had 1 parameter in this dimension 1 that was for the selection of the climate. To now make something that is a little bit more fancy to examine, I would like to do more than 200 simulations. So my suggestion here is to extend this by taking 1000, and we will see how much time it will consume. This is of course always a problem when you would like to run your models, that the more you add, the more demanding it will be to the resources. And when I start this, you will see that it has to do now 2000 runs, and yes, during the time I've been starting to speak, it's up to 100. So it's not that terrible, but before we said that you need a coffee break and you could relax for a while when the computer is making the thinking, and you could do something else. So a small break is sometimes also good for us when we are looking to those results that we can produce by the model. Another good thing with this type of, we can say, shifting between looking to a simulation and producing a new is that we could create up our imagination. We could start to prepare ourselves if the results will be what we expect. And if that's the case, then of course we could say that then we feel that we are familiar with what we are doing, and we feel confident just because our thinking is consistent with the model. But it may be also the opposite. We remember now that what we had in the previous run was, of course, many patterns that were not that good, but we also have to realize that we have not been looking to the real conditions. We have not been digging in the soil, we have not been taking any samples. We are just playing with those properties, and then we try to tune the model to more realistic behavior. And many people, they feel that this is wrong. We should instead not go to this calibration. It's much more reliable to, first of all, make single runs, one run representing change in only one single parameter, because that is, easy to follow. But when we are changing many things at the same time, then there are so many combinations and we don't know how to look to it. When this simulation is complete, we should also look to a little bit how we could examine the sensitivity of the parameters, not only for the performance, but also for how it affects the results. In some cases, those uncertainties are extremely important for the performance, but not at all important for some of the outputs. So for instance, if we would like to estimate the runoff, how much water is leaving the system, it may not be affected by the parameters, not even by the performance, because all those parameters are not creating such a big impact on what is creating the error in the water balance. So it's also important to say that when you are doing this calibration, you should have realistic expectations. Too much of thinking that you are getting great results that will prove how your water balance looks like may not at all be correct, because it might be that the only thing that you have been changing is how well you look to the performance. Okay, we are now ready, and we could go into our new document, and I will quickly look into some of the outputs. And if we go to this validation, and we can start with making now an estimate of the mean value for the full ensemble. Then we can look to this for the saturation level, and we see something like this. We see that now it is much more dynamics through the whole period. So we have something that is substantially better than before, at least in the potential. But if it is also better in the particular performance, for instance, looking to the statistical, we can say that the R-square is like this. It is from 0 to 0.9 more or less for this saturation level. And if I look to the same for the other, it is also similar. So it's quite interesting results to constrain, because some are extremely bad and some are reasonably quite good. We can look also to those that are the mean error, and then no, sorry, I will clear this, and then I will not take this from the beginning, and then we see that the mean error is systematically above, but not so much for the first, and for the second it is around 0. This is actually what we would like to see. The prior is more or less on the same deviation from 0. Here we have it still systematically above. So we could have extended the range to make it better here. But in this case we have it very nice. So location 3 is still a perfect, but location 4 could have been adjusted, and then the only way to adjust that with respect to the magnitude is to extend the range of the parameter. Okay, but this is still not that bad, and what we can do now is to continue and to see if we could constrain an ensemble based on those results. And then we have this evaluation multi, and in this evaluation multi we could take any one of the different performance criteria and use that to take only those that are good enough. This time maybe we can take this LogLikelihood. LogLikelihood is, what is used in all the Bayesian calibrations, and the good thing with that is that it's only looking to the probability, and the less uncertain the better. So we can request here to take for location 4 only the 10 best. We keep the 10 best, and then it estimates a value that constrain it to only 10 of the 2000. If we would like to do that also for location 3, we can directly say that it will not be very easy, because when location 4 became good, location 4 became very poor. So we have to keep them separated if we should try to optimize them. And then we have a good opportunity here in this evaluation, and that is not only using one ensemble, instead we could use 2 ensembles. And I can do that if I go to this heading where I see that this is based on the normal transformation, and then there are many possibilities to create new ensembles, and also to create new ensembles with transformed data. Actually, I would like now to make a new ensemble on the same type of data, so I don't want to put anything new. I just add new ensemble for setting of new criteria. So that's it. So now we have ensemble 2, and now we have again 2000. And if I then can take the opportunity to constrain that in the same way for the one from location 3, I visit that line for location 3, right click and then I keep the 10 best. And then I should get the 10 best for that location 3, and then I also notice when I look here that that gives very poor results for location 4. Okay, now it should be good for one location for one ensemble and good for another location for another. We go back to our simulation document. We estimate those means for the ensemble, and then we make a chart. And now the chart could make it a little bit more. Actually, I can actually move this to the bottom line. Now you see, we have 2 ensembles, and one is high and dynamic, and one is low and less dynamic. And those can be compared with the measurements, and then we have the green line showing relatively good performance with the red band of this ensemble 1, and the next, extend this, so yeah, we had decreased to 4 small charts. Now I make the full size of the charts, and then I also would like to extend this measured value, and then we see that we got the measured value for location 3 here, and that's also following now quite nice. So we have been successful in my view, and this is not maybe too mysterious, but we had the advantage of having one model that could be compared to 2 different positions, and there were no chance to get the model to be good for both, but we could explain the difference from one position to another by those parameters that we have constrained. So the question is now, how does the parameter looks like? To examine that, we can go back to the sheet for the Multirun, and then I will show that a little bit more, because here we have a table now, and then it shows now ensemble number 2, and it gives some values for those parameters. And you could see that this red one is a high value and a blue one is a very low. So some have been constrained to the upper range and some have been constrained to the lower range. If we would like to look to the distributions of the parameters, we can click to them one by one. So for instance, I click to this drain level now, and then we see that we have all the variability of the parameters for the 2000 runs, and then we have one blue. That is the one that have been constrained by ensemble 1, and we have one green here in the background constrained by the ensemble 2. So it looks like, it could have been even better if we could have allowed this to go lower. So maybe the next we should go down to minus 1.2 meter and not only 1 meter. If we look to another parameter like air entry, we can also see that it looks like the 2 ensembles are partly deviating in the same way, but not so obvious now, because this blue one is also taking very high value, and the green one is mostly high values, but not systematically. So we have 2 parameters that have been constrained, but I think this drain level were probably more strongly constrained. If I look to in it temperature, it's not so easy to see, but it looks like they are in both ways. We could actually view this in another way, and that's done by going to this short actions. So if we pick that and we can put that on the top here, then we see that we are now looking to this as the short type of time series, but this could be shifted to something that is more easy for looking to how it looks like. I look to now cumulative frequency distributions, and then you see another where the probability from 0 to 1 is on the y-axis, and the parameter values are on the x-axis, and you see both seems to be a little bit to the left, and that's maybe interesting, since this temperature should not have so strong impact on those constraints that we have done by the groundwater. We can look to the other parameters in the same way, and then I will just click on the X here to get more charts. So I will take 4 charts now, and then we look to the initial groundwater, and we look to the total conductivity, and we look to this optimum value for the leaf area index. And then we see that the total conductivity is also quite different for the 2 ensembles. Ensemble 1 with the high and the other with the low. So they may indicate that we have different hydraulic conductivities at 2 locations, but it can also be some other parameters that is connected to that. So obviously I will also take the drain level in the same, take one more here, and then you see the drain level, and that was very strongly constrained. The blue line is, all to the left, and the green one for ensemble 2 is somewhere in the middle, but strongly constrained. Like, of course, the initial groundwater, it's something wrong with the scale here, but forget about that, because that is the same as the drain level. So at least 2 parameters was very well constrained, and we can also say that when we have got these results, we have got something that could be further examined on many different ways. I said that we were interested in the sensitivity, so of course this drain level is a crucial one, and if we would like to see this and how it influences something else, we have also an option here, so we can right click and then we can set this as the first independent variable, and then something shows up here. And that was, I think, a mistake, because I happened to click to another. So I remove the variables. So now I have the drain level as the x-axis, and I would like to jump over to look to, for instance, the performance. And then you could see now the drain level will be on the x-axis and some others will come on the y-axis. So this was the previous, so I will clean this again. We can take, for instance, this is now plotted in the scatter way. Okay, this was not exactly what I expected to see. How comes? Up. I will just check this now. For the Multirun should have this drain level. Maybe it was not the very best choice because the drain level has not. Oh, there's something wrong with this. We can take another candidate. We go to this air entry. I'll put that as the first independent. And now we see air entry here. And now we see the mean error. So now I think we have a better and correct way to show those dependence. I will actually return in the next video to examine this in more detail, because now we have been keeping on quite long and we need a break, and I need to sort out why I couldn't get this to be exactly as I expected in the end. But the new issue in the next video would also be that I would like to look a little bit more how we can predefine those options, and this is a way to predefine the criteria for learning, and learning is connected to AI. So the use of, for instance, this LogLikelihood is a way to select the good ones and to use those in the future for the next estimates of the behavior. So this will be the subject for the next, and now we will finish this for this time. Thanks for listening.